is the module 1, module 2 focus. So again, keep that in mind. If our focus is on the time response, that means we have to solve for these equations. And a couple ways we can solve for this one. The first one is we directly solve for the differential equations using your differential equation techniques. Okay. And sometimes it's time consuming, but sometimes it won't, and it depends on your how familiar you be with these kind of things. But most of the time in controls, we like to take the Laplace transform, which could be the second solution process to those equations. Okay, and there's a couple of reasons. The first one is the Laplace transform is easy, and we check up against the tables. We can find always the transformed counterpart, and then put everything into algebraic expressions of the differential equations. Okay, and so here, before we kick into the tables, here is a quick examples. I won't go into details, but give you the big pictures here. So this is the differential equations. Physically, basically, it can be one typical single degree of vibration systems. Okay. So the way it did is this: we take the Laplace transform on the whole equations. So that means we take the Laplace transform on the individual terms, okay? And then we put into here. And so basically from here, say we take the Laplace transform of the x, that is a function of t, that is a time domain. If we, for some certain form that we define as the x of s, this is counterpart of the x of t in the s domain. S domain, S is the variable we use in the Laplace transform. Okay, so basically everything here, this is the x of s. And that one can be converted into multiplied with the coefficients in the polynomial of s. And then with certain algebraic terms, another algebraic terms, this one is the Laplace transform of this particular term here. Okay, but anyhow, from here you can see we can express x of s in terms of those things. And then the next step, we simply take the inverse Laplace transform of everything, and we convert back into the time domain. So that means we take the inverse Laplace transform of this, and this individually, then we become this. And the plus inverse of this term will become is this. So that is the solutions of the x of t. Okay, if you take the solution process from your differential equations to solve for this one, you will get this one as well. Okay. For this case, the solution process has included the boundary, the initial conditions here. So we plot the response. So that is the response in controls. We are concerned about what is the steady state solutions, the value here. And what is the transient response, which means how quickly the solution will respond to which level, and etc. Okay, so that means here the goal is, the fundamental process is to get this one done. Then from there we begin to look into the system response, and then begin to design the controllers as well. Okay, so that is the first reason we want to learn how to apply the Laplace transform. And the second one is with this form in terms of S. We will be able to use block diagrams. That is a standard language to describe the control systems. With the block diagram, we'll be able to apply certain techniques like the transfer functions and to do something. And from the transfer functions, they do have the further extended information like locus. That will be on the module 3. Okay. And then from the transfer functions, we'll be also able to study the frequency response will be the module 4. So basically here, in terms of the Laplace transform, that form a very good foundations for almost everything we're going to learn in this semester. So that is the big pictures and review of the Laplace transform. And here I give you the quick review of what the Laplace transform is. So by definitions, the Laplace transform is this. Whenever you have the function of time, and you simply plug into these integrations and do the integral, if the integral and the value of the integral exists, which is doesn't approach to infinity, then we have we call the transform exists. And basically you can see this integral is integrated about t, so leaving s as the variable here. So that is the function of s. Okay, so usually our symbols, the convention is this. We use lowercase, for example f, to indicate the function in the time domain, and using the capital of that letters to indicate its counterpart in the S domain, which means Laplace transform terms. Okay, so that is the things. So we can look at this form and we see what happens. Okay, so if you want to do that one manually without referring to Laplace tables, then you can do it like this. So for example, we plug in. Okay, so f of t right now is exponent of at, and then we follow up and by copying the remaining informations. Okay. Do this integral. Everyone should be able to do it. Otherwise, okay. And so for this one, this is the indefinite integral, and I simply take up a special techniques. Is this? I simply put this as a k, and I have the k approaching to infinity. Okay, in the way I can deal with the whole things, a minus s over t and t. Okay, so for this one, then basically that is the limit k approaching to infinity. This one is how much a minus s1 and e minus a as t, and t is from 0 to k, and k is approaching to infinity. So why not at this moment, let me take out this one, then replacing k by infinity. Okay, so this one you do it correctly, this term should be minus, so that will be s minus a, 1 over s minus a. Okay, so that means here we build up the table. If we have the functions, and which is in the EAT, then is the Laplace transformed will be 1 s minus a. Okay, and then we can repeat other things. So for example, e minus at, then that will be s plus a. Okay, continue. If we have psi t, then you can continue to do the integral and then give a try. Then psi t then will be equal to s squared plus 1, 1. Okay, give a try. And I know the answer, so I directly copy it here. But this one will be the simple function. You should be able to do these things. But in this class, that is not our focus to learn how to do the integral. No, everything will be tabulated. So that is the today's handouts. Today we have one page of handouts, and probably can cut it now.